What's up, guys? When you took pre-calc or algebra 2, I'm sure your teacher taught you what the natural log was, or at least a log at that. But when we were in algebra 2 and pre-calc, we only really used logarithms with positive numbers. But now, what if we expand that to our negatives? Let's see, we have -1. Yeah, I think that's a good basis to go over for first. But to figure out how to find a negative logarithm, we're going to have to go through a couple of steps. Um, but it'll be fun. Let's get into it. For some reason, I made this transition way too long. Okay, there we go. All right, first we're gonna start. What's a Taylor series? So I think we should define a Taylor series as an infinite polynomial or an infinite degree polynomial, which we can use to approximate a function. We see that if we have to center our function at a point, and essentially we are taking an infinite degree polynomial where we're following a formula where we multiply our function evaluated at our center point, which in this case would be a, and we multiply, depending on degree, the degree of x minus our center point to the n minus 1. And then we multiply, as we keep going through, we multiply it by the nth degree of our function evaluated at that center point. So if we look at our example, we have f of x centered at the point A is equal to f of a multiplied by 1 plus f prime of a multiplied by x minus a plus f double prime of a multiplied by x minus a squared over 2 factorial. So essentially, what the formula follows is our sum from 1 to infinity of f of the nth derivative of our function evaluated at our point of center multiplied by x minus our centered point to the n minus 1 over n minus 1 factorial. Now, let's delve into a more specific type of Taylor series called Maclaurin series. So the Maclaurin series is essentially a Taylor series, but we center it at 0. This is essentially the most simple type of Taylor series to work with when we're evaluating functions, and I think you'll see why in a bit. So, let's look at e to the x. And let's try to form a Maclaurin series for e to the x. So we have our f of x equal to e to the x, and we have our first derivative of e to the x equal to e to the x, because e to the x never changes when you take the derivative of it. And so, if we evaluate all of our derivatives at 0, we get that it's 1, because e to the 0 is 1. Yeah, simply. So, when we form that Maclaurin series, we will see that e to the x equals this. And this is a very simple Maclaurin polynomial where it follows our pattern of the summation from 0 to infinity of x to the n over n factorial. But let's go. I have an idea, and let's work with this Maclaurin series, because when you mess around with e to the x, we can get some cool things. So let's go imaginary and let's add an I there. So let's go e to the ix and let's see what happens. So now when we form our Maclaurin series for e to the ix by simply replacing x with ix, we get this formula right here, where we have the summation from 0 to infinity of ix to the n power over n factorial. And when we simplify that, we end up getting this we end up having this Maclaurin series, because you have to recognize that I squared is negative 1, I to the third is negative I to the fourth is positive 1, and on and on and on. So we can actually simplify that and get rid of some of our i's in our series. And so now let's take a moment and let's group our imaginary part with our real part. So now when we form a series for each one, we see that our real part follows a series of from n is equal to 0 to infinity of negative 1 to the n multiplied by x to the 2n over 2n factorial. And our imaginary part follows the summation of negative 1 to the n multiplied by I multiplied by x to the 2n plus 1 over 2n plus 1 factorial from n is equal to 0 to infinity. And let's simply just factor this I out because we just can, because it's, not really part of our sum. So now we have factored this I out. Okay? So let's look at two other Maclaurin series that will be helpful to get to the point I'm trying to get to. So we're gonna look at the Maclaurin series of sine and cosine. But first, let's just take a look at the Maclaurin series of cosine. We see that our function is equal to cosine. Our first derivative will be negative sine. Our second derivative will be negative cosine, and our third derivative will be sine. So let's write out our Maclaurin series, okay? And our Maclaurin series, we're going to evaluate all of our functions at 0. And so we get this polynomial. And then let's simplify this, and then we can make a general term, or a general formula for our series. So we have cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus plus until we get the sum of n equals 0 to infinity of negative 1 to the n multiplied by x to the 2n over 2n factorial. So there it is, our series for cosine of x. But it looks similar to what we saw, right? It looks similar to what we saw in e to the x. Interesting. All right, well, let's get rid of this polynomial. Let's get sine of x. So we have f of x is equal to sine of x, f prime of x is equal to cosine of x, f double prime of x is equal to negative sine of x, and x triple prime of x is equal to negative cosine of x. So let's form our Maclaurin series for sine of x, and let's evaluate all our derivatives and our function at 0 to get this polynomial. But when we simplify that, we see that sine of x gives us this polynomial, right? And we can see that our general term is the sum of from n is equal to 0 to infinity of negative 1 to the n multiplied by x to the 2n plus 1 over 2n plus 1 factorial. Looks familiar, doesn't it? So let's bring our Maclaurin series for cosine back up here. And let's look at our series for e to the ix. So, if you haven't realized by now, if we look at our grouped series in e to the ix, we can see our real part follows the Maclaurin series of cosine of x, and our imaginary part follows the Maclaurin series of sine of x. Sorry. So let's do some simplification, and let's substitute. And so now we get this cool expression: e to the ix equals cosine of x plus I sine x. So if you know how trig works, you'll see we can do some interesting things with this. So let's substitute pi for x. And we know that cosine of pi equals negative 1, and I sine pi, or sine of pi, is 0, so that term is going to cancel out. And so we get e to the I pi is equal to negative 1 plus I times 0, which is just negative 1. This is Euler's identity. I'm sure you've heard it around, but this is how we actually derive the identity. So we have e to the I pi is equal to -1. But you also have to recognize that trig functions cycle. Every 2 pi radians, the function cycles back to the same value. So actually, we can expand on this definition, and we can add 2 pi k I pi, where k is in any integer, or yeah, where k is any integer. And so we can factor out this I pi, and we can make a general formula for -1, and we see that -1 is equal to e to the 2k plus 1 multiplied by I pi, where k is any integer. So now we can take the natural log of both sides, and we can see that the natural log of 1 is equal to 2k plus 1 multiplied by I pi, where k is any integer. So now let's get rid of this, and let's just take a moment to look at the property of logs. So we have three main properties of logs that we learn in school, or learn in algebra or pre-calc. We know that the natural log of a times b is equal to the natural log of a plus the natural log of b. The natural log of a divided by b is equal to the natural log of a minus the natural log of b. The natural log of a to the b is equal to b to the natural log of a. But in order to come to our conclusion of taking the natural log of a negative number, we need to focus on our first property, where the natural log of a times b is equal to the natural log of a times b. So let's bring that to the center for a bit, and let's hone in on that. So what we're first going to do is we're going to look at the natural log of -x. And before I go into it, I'll pause for a second so you can think about it, and you can understand how a log or a negative logarithm will happen before I show you how. All right, let's go into it. So the natural log of -x, we can imagine this as the natural log of -1 multiplied by x. You see where this is going? So now we can say that this is actually equal to the natural log of x plus the natural log of -1. And cool thing, we know what the natural log of -1 is. And we know that the natural log of -1 is 2k plus 1 times I pi, for where k is an integer. So we could say that the natural log of -x is equal to the natural log of x plus 2k plus 1 times I pi, for k is any integer. So now let's go to an example. Let's look at the natural log of 2, where 2k plus 1 times pi is in the bounds -pi to pi. Or the argument is z, but we'll delve into notation like that in the next video. But first, we see that the natural log of 2 is equal to the natural log of 2 plus the natural log of 1, because that's how the properties of logs work. And so then we see that the natural log of 2 is equal to the natural log of 2 plus 2k plus 1 times I pi. So, since we're in the interval -pi to pi, and -pi isn't defined in our interval, we must have 2k plus 1 times pi be equal to pi, and the only value of k for which that works is 0. So let's substitute that in, and we get the natural log of -2 is equal to the natural log of 2 plus 2 times 0 plus 1 times I pi, which simplifies to natural log of -2 is equal to the natural log of 2 plus I pi. Well, there, we did it. The natural log of 2, for where 2k plus 1 times pi is in the interval -pi to pi, is equal to the natural log of 2 plus I pi. Well, that's all I had to offer for you guys. thank you for watching this video. I put a lot of work into it. Took me like 288 lines of code to animate this, which was a pain in the butt, but it was fun, and I got to get into a cool concept like this. But this is just the first video of a series I will be posting. Um, this is just basic complex logs where I will be talking about the natural log of negative numbers. But in the next video, we'll delve into something a little bit more complex, where we'll now take the natural log of a complex number rather than a negative number. So I hope you'll watch that one, and I thank you for watching this video. Goodbye.